and today I'm going to tell you everything you need to know about how to find the derivative of exponential functions. So let's consider our function f of x equals to e to the power of x, our exponential function. And watch here as the magic happens. We're now going to take the first derivative of our function e to the power of x with respect to x. And what do we get? We get e to the power of x. That's amazing. So the derivative of an exponential function is exactly the same as the original function. However, we have to consider some cases where we have more in the exponent instead of just x. What if we have, for example, e to the 2x or e to the x squared plus 7? This is where we have to use a combination of derivative rules with the chain rule in order to find the final derivative. So let me show you the general way how to find the derivative for any function g of x. So let's say we have some function. We're taking the derivative of e to the power of gx. So instead of just having x in the exponent, we now have g of x in the exponent. So we can see that this is a composite function. So the e to the power of x is like our outside function, and then our g of x is our inside function. And whenever we have outside and inside functions, we always have to use chain rule. So let's look at how we're going to take the derivative. So recall that chain rule is the derivative of the outside function multiplied by the derivative of the inside function. So if we take the derivative of the outside function, that's e to the x. So in this case, our x is g of x, and that stays the same. So remember, derivative of the outside function while keeping the inside function the same, multiplied by the derivative of the inside function. So we found this over here by our chain rule. So you can use this in every case to find the derivative of these composite exponential functions. So why don't we go and do an example to see what that looks like in action. So we're going to consider a function f of x equals to e to the power of 3x. So we've identified here that our outside function is e to the x, and our inside function, our g of x, equals to 3x. So again, we have this inside function over here that's been wrapped up in our e to the x function. So now we can use our definition that we just created. So f prime of x equals e to the power of g of x multiplied by g prime of x. So I always recommend to write out your definition first. So we've written out the definition of our derivative. And then secondly, I recommend to calculate every component separately, and as a final step, add it or sub it all into your definition. That actually helps you reduce errors, and it helps you organize your thoughts in all the components of your equations, especially as you get larger equations as you go on in math. So we've said that our g of x equals to 3x. So let's write that once more. So g of x equals to 3x. Let's look in our definition here to see what else we need to find. We also need g prime, our first derivative. So here we can use power rule, so we get that our first derivative equals to 3. So now as our final step, let's just plug all this back in to our definition to get the answer. Therefore, we have that f prime of x equals to the e to the power of 3x multiplied by 3. So we can rewrite this in a more traditional way so that we have the derivative equals to 3 multiplied by e to the power of 3x. And there we had it. Now we learned how to solve exponential functions that have composite functions. So exponential functions that have functions in the exponent. So that was really fun. We're going to look at one other case. So in my previous video, I showed you how we deal with logarithmic functions if they have an arbitrary base. So be sure to check out that video because log functions and exponential functions really go hand in hand as they are inverses of each other. So I'm going to show you how we can find the derivative of an exponential function with an arbitrary base. So that means we have f of x equals to a to the power of x. So make sure we note our restrictions. So a has to be greater than 0 and a cannot be equal to 1. So previously we had our base was e. Now our base is a. How can we do this? So I'm going to give you the definition of the derivative right below. So the derivative with respect to x of a to the power of x equals to ax ln a. So again, we can see how our logarithms come in. So just as an aside, recall that ln a equals to log base e of a. So ln is a natural logarithm. So this is the definition. Now we have to also look at the more general case where we might have a composite function where we would have another function in the exponent instead of just x. So in that case, we have our function is f of x equals to a to the power of g of x. So again, we're going to apply our magical chain rule, which will help us find the answer. So let's go through this process. So the derivative with respect to x of a to the power of g of x equals to a to the power of g of x multiplied by ln a, and then this whole thing is multiplied by the derivative of our inside function, which is g of x, so multiplied by g prime of x. So let's compare the two. So we can see that it's pretty similar. So the only difference here is that when we had just x in the exponent, we have x over there, but here we have g of x. And then because we have a composite function, we then have to multiply by the derivative of the inside function here. We're above, technically you can think about that the same way, but the derivative of our inside function x just equals to 1. So be multiplying by 1, and that's why we don't have to show it because it won't change our function. Okay. Let's go ahead and look at an example so we can see this new rule that we learned in action. Okay. So we have a function f of x equals to 4 to the power of x squared plus 1. Whenever you encounter a new problem, I want you to think about what you're dealing with. Okay, first thing you say to yourself is, I have an exponential function. The base of my function, the base is 4, and then you can think of what is your exponent. So here in my exponent, I have x squared plus 1. So this seems like a whole function on its own, so we can call that our g of x. That is our inside function, and here our base does not equal to e. So that means we have an arbitrary base problem, so that means we have to use the second theory that I showed you. Okay, so let's go through and apply that. So we know that the second formula I showed you is the derivative with respect to x of a to the power of g of x. So we've identified it's this case with an arbitrary base and it's altogether a composite function. So this equals to a to the power of g of x multiplied by ln a multiplied by g prime of x. So again, write the definition out, solve for all the individual pieces, and then put it together. So let's look at that. In this case, our a equals to 4, our g of x equals to x squared plus 1, so then our g prime of x equals to 2x following the power rule. So now we have everything we need, and let's go ahead and plug that in to our definition. So therefore, our derivative f prime equals to 4 to the power of x squared plus 1 multiplied by ln 4 multiplied by 2x. And there you have it. We've solved the derivative. Thank you all so much for watching. If you enjoyed this video, please drop a like below and comment any questions that you have. I look forward to seeing you next time.